Good morning, and it's a pleasure to address you this morning. As Pete introduced me, I'm actually a mechanical engineer, so I'm not a medical practitioner, and I have about 35 years of experience in engineering as such. And what I'd like to address about this morning is the similarity to how a medical practitioner would approach a patient and assess what the risks are versus the outcome of the patient and what treatment to actually propose. We use a very similar process in risk assessment of facilities to ensure that we weigh up the risk on the one side versus the best outcome for the patient on the other side. The most important message I want to leave with you this morning is we can comply with the rules, but unless we understand what the real risks are in our facilities, we cannot achieve the safety that we require. Okay, the key questions I would really like to propose to you this morning, and hopefully by the time my presentation is finished, you can answer these for yourself. And the first one is, how do you actually determine whether your hyperbaric facility is safe? And please don't tell me that it's by compliance with the standards. We have to find another way, because every facility on this planet differs in some other way. And then what do you do if your facility doesn't comply with the requirements? How do you then approach that? You have theory on the one side and you have a really practical issue on the other, and you have to make a real decision, and sometimes that decision is outside of what the rules tell us we can do. And then finally, and really importantly, how can you demonstrate that you've done everything you can to ensure your facility is safe? And this comes up in the accidents, and the accident reviews and the various investigations and even court cases where we find that when it's too late, we haven't really done what we should do, and even if we had, how do we convince the prosecutor and the jury that we've done everything we should have done before that accident happened? And we call this the risk assessment process. Similarly to how you practice medicine, we need to use the same principles in ensuring that our facilities are safe. A couple of graphic reminders to you here that what we're talking about in safety can be pretty catastrophic if things go wrong. Some of them I can introduce to you. I think you all know the one up on the left at the top, the one they had in Italy, and then the one in the middle at the top is the one they had in Japan. And you can see the Japanese chamber physically exploded as a result of the fire. We tend to fixate on fire, but it's not the only issue we have to deal with. And the one on your right at the top is the not well documented, but I think most of us know about the explosion in Reunion, where the door came apart on the front of the chamber and actually devastated the front of the hospital. And then back to fires, we had, unfortunately, a fire in South Africa where the doctor who was inside the chamber happened to be one of Burma's researchers, so he was really well acquainted with the risks, and yet he went and did things that are clearly not safe. The well-documented case that they had in Florida, where last year they finally settled the case. This happened in 2009 with pretty devastating outcomes, and they were Italian grandmother and child that were in the chamber. And then, if that's not enough, there's a really stark reminder. About 6 weeks ago, we had a significant fire in Jakarta in Indonesia, killing some high-ranking people in the Indonesian Navy. We're not sure whether we will really get down to the bottom of what happened in that case, because politically in different countries, they either prepare to expose what happened in some cases, with pressure on them to actually just write that accident as something that they couldn't have prevented. And then, of course, it's not just about the equipment, but there are people involved in this. And it's an interesting observation to make that mankind exists at the moment in the safest environment that we've had since our initial creation. And yet, with all of the knowledge we have, we still feel relatively insecure. The more we know, the more we fear when things can go wrong. Now, we have a good range of publications and guidelines out there to guide us through this process. Some from the United States, some from Europe, but they tend to address only certain aspects of our facility, and they don't really account for the fact that every facility will have a different staffing, different location, different type of patient that they get to treat. Then we have the safety, yesterday we referred to the safety manager, some people prefer to refer to the safety officer in an occupational health environment. And in the US they talk about a safety director, which is to some extent a misnomer, because that person shouldn't be the one making the final rules or final decisions. That rests upon the medical director. And the medical director has been proven in history to be the legally responsible person when things go wrong. And yet, and with all respect to you, You don't always have the training and the understanding of the technical issues that one has to deal with. You leave that to the engineers, hopefully. So we need to find some objective, practical way to actually make sure that in a real sense we comply with what we call realistic occupational health and safety principles. So it's not about the theory, it's about what we understand, and we need to make sure that we comply with the real situation. So enter the risk assessment process, and this is certainly not something new to you, and in terms of occupational medicine, very well documented. We start off with our hazard identification, looking at theoretically what are the dangers in our facility and in the way we run the facility. And then we have to take that hazard and turn it into something that is real for us. Is it actually a risk, or is it not a risk to how we run our facility? And clearly, once you've identified the hazard and turned it into a risk, and we will speak a little later about how to determine the priority of that risk, we then need to mitigate it. We need to put in some steps to make sure that we cannot then have an exposure that will lead to something we don't really want to see. And then we don't stop there. We need to monitor the decisions we've taken to make sure that they have the effect that we need them to have. And very often we will be monitoring how we've approached this and have to go back to our risk assessment and go back to our risk mitigation. So it's very much a dynamic and iterative process. So let's have a look at the elements of this HIRA program we're talking about. So we start with the hazard identification. Now, none of these hazards up on the screen are unique. We have exposure to high pressures. We have very defined and history-proven fine explosion hazards. We have restrictive environments. We have an issue inside the chamber. You cannot simply open the door and get access to the patient, and in a monoplace chamber, even less so. Then we have a range of mechanical and physiological elements that we're concerned about and we need to review. And then we operate in potentially dangerous equipment, high-pressure pressure vessels, compressors, pumps, and so on. But what is unique in a hyperbaric facility is we have all of these hazards working in combination, and we then have to approach this in a different way to simply identifying one and addressing the one hazard. We get some guidance in the NFPA 99 publication, which is a very well-known, well-developed publication from the United States. They have an appendix on what hazards are present in a hyperbaric facility. And then we have what we call the Risk Assessment Guide, which is a document that we developed out of our approach to safety in South Africa, where we're looking at not just what hazards are there, but are they related directly to the different types of chambers we have. And another reference is the Hyperbaric Facility Safety Compendium that was put together by Tom Workman, but drawing from the international environment and getting a much broader perspective as to what hazards exist out there. So we define our hazards into three categories just to make it easy, so that when we approach something, we can already determine what does that hazard affect. And the first is fire and explosion. It tends to be the most dramatic one and the one that we've had the most recorded incidents around the world. And specifically looking at the one in Japan, the one in Italy, these are pictures I showed you before. They had one significant one in Florida in the States, and then we've had one in Peru, not that well documented, and there's a lot of speculation as to what the cause was. We had the dramatic one in South Africa, which we're not very proud of, and then recently the one in Indonesia. So clearly this is an issue. And then in terms of mechanical hazards, we had the door that opened under pressure in Reunion, killing the engineer that was working in front of that, so we have to take care too. It's not just the people practicing the medicine. And then we've had one or two documented cases in the offshore environment where windows have come apart as a result of overheating and rapid depressurization, never mind hurting people on the outside, clearly catastrophic for the people on the inside. And then in terms of physiological or health-related hazards, I might have introduced this one to you. I'm not sure how many people know about the accident they had in Mexico last year, but essentially they left the patient in the chamber and went home. This is a monoplace chamber that stripped everything off, and the patient was stuck inside the chamber and clearly asphyxiated. The only good thing about that was the next day when they discovered what went wrong, the police arrested the nurse and the doctor and took them straight off to jail because they were clearly taking this thing very seriously. It's a terrible way to die. And then many, many years ago in Hanover, during air treatments for a variety of conditions, they essentially went down too deep and caused everybody inside the chamber to suffer decompression illness. And some of them passed away as a result of it, and some of them they managed to get back and decompress them safely. And then we've had rapid depressurization in the offshore industry, and then we had a significant suction injury to a diver that was on the toilet when he then exposed his sensitive parts to significant suction. And fortunately, they managed to send a surgeon into the chamber who then did a resection on his bowel and actually survived the accident, but fairly significant and dramatic. Okay, let's go through these in just a little bit more detail to get a handle on what we're talking about. And fire and explosion, we know, is the greatest risk simply because it's the most dramatic and the most recorded one. The theory tells us we have what's called a fire triangle. A fire doesn't just happen spontaneously. You need to have oxygen, and we cannot avoid oxygen. It's a treatment material. Fuel, so something has to burn, and you need a source of ignition. So we can focus on these parts of the triangle to try and break the triangle and make sure that we don't end with a fire. And then if we do have a fire, we have a range of complications. Obviously, we're going to deplete the oxygen. We're going to overheat the breathing gas so that the more the person breathes in the chamber, the more damage is done. Clearly, when things burn, they produce toxic vapors and toxic products. And that generally tends to be the part that actually leads to a loss of life. Then we'll have thermal burns to the patients inside there. Most of the cases, the burns tend to be fairly superficial if they can get the chamber turned off in time. But the one in Florida, we saw very significant burns. And then rarely, but we've had 3 documented cases of pressure vessels will physically explode as a result of the fire. We do, as engineers, try to build into the design of a chamber what we call a fire case. That if there is a fire, the chamber should not explode. There should be other measures that can prevent that from happening. And remember that when we do have a fire in an oxygen-enriched environment, your response time is critical because you don't have a lot of time to actually react. And of course, we can't open the door and get in there with a fire extinguisher, get the people out. In terms of mechanical hazards, just briefly, I think most of these make good sense to you. We have a lot of energy stored in our pressure vessels inside the chamber, in our storage vessels, in our high pressure bank. Then we have limited access and limited visibility. We cannot always see what is going on in the chamber, and certainly behind the chamber, on top of the chamber, underneath the chamber, in the compressor room, you don't have good access and good visibility of what's going on inside there. We have machinery that is operating that is hazardous. We have heavy loads, and typically this will be people moving cylinders around and patients that are perhaps overweight, and these obviously are hazards to us. Many pipes and cables and hoses around, so we end up with potential to slip and to trip and objects falling down. We take equipment into the chamber, we expose it to pressure. That equipment wasn't designed for that, and the equipment then fails as a result of pressurization. Or it implodes on the way down because it's not vented correctly, or it explodes on the way back to the surface because gas is trapped inside there, similar to how you might trap gas in your lung. And then we have a range of ergonomic issues, repetitive actions, nurses especially having to open and close doors or tighten or loosen something, and they'll end up obviously with strains. We have lighting issues, noise issues, and so on. And then the one you're probably the most comfortable with are the physiological hazards that we have. And the one at the top is probably the greatest cause of injury at any hyperbaric facility. Nurses and staff picking up heavy patients to get them into the chamber, to get them on the stretcher, and injuring themselves in the process. We can have too much oxygen in the chamber or too little if you're not paying attention to how we're ventilating and what's consuming oxygen. Clearly rapid depressurization if a valve were to fail, if a window were to fail. Decompression is fairly well documented that we end up bending our tendons and our tendons because of either poor planning, poor management, poor operating, or their physical condition before they go into the chamber. Most of the multiplace chambers that you used to here in Europe draw in air from the outside, and it's possible to entrap pollutants into that. Bear in mind that our filters are not generally designed to take out carbon monoxide, carbon dioxide, and some of the other lethal gases. Only if we know about them can we then build in a filter to remove those contaminants. We have a lot of electricity around our chamber, and we have a nice big steel hull that makes sure that if we have a leak in the electrical system, we're going to be electrocuted. So we have biological and toxic issues from disinfection and from other inappropriate waste disposal. Heat and cold. Chambers get very warm when we pressurize them, and very cool when you take them to the surface, and some patients don't like that exposure. And then we have noise. Because of the higher pressure, the impact of that noise as a result of the denser gas is more significant than it might be at the surface. Okay, so we have a good background as to where to look for the hazards in our facility. Now we need to take that theoretical hazard and decide how it applies to our approach to safety. And a good definition that we like to use in this occupational health definition is a risk is defined as the probability that you will have some exposure to that hazard and that will lead to negative consequences. It's not a single dimension, it's a multiple dimension, and we need to look at all these aspects when we do our risk assessment. The hazard is the theory, it's any potential risk to the patient or to our staff, and that allows us to then think very laterally and think potentially what could cause us a problem. We need to have an exposure. If we don't expose people or equipment to that particular hazard, clearly there's no risk there. So people will relate to us from the standard, this is the possible hazard, but it's impossible to get an exposure to that. Then we have some element of chance. What is the likelihood that this exposure to that hazard is going to cause an incident or an accident? And then we have the consequences. And if the consequences are very mild, then we don't need to get too worked up about it. But if the consequences are severe, clearly the weight of that risk will increase significantly. And we're going to take those factors and multiply them with each other to come out with some way of providing priority to us as to how we should address these risks. Okay, once again, many publications out there that we can draw on to identify hazards and to try and address some of these. And we need to take that information, we need to take the reality of our situation and turn that not into compliance, but a process that we can then decide, do we really have a risk? And what is the magnitude, the importance of that particular risk? And then we apply this to our chambers, and they vary hugely as we travel around the world. Some of you might recognize some of these chambers, those of you that do a lot of diving in some of the areas, and some of them are fairly stuck away, but we have them on dams stuck in East Europe or in Latin America where they're doing a lot of diving to fix the hydropower station. So places that you might not expect you to get decompression facilities and hyperbaric facilities, you do. It doesn't matter what the facility looks like, the process is the same. Okay, let's take that information and use it to quantify how important that risk is and why we should or shouldn't worry about addressing it. And this is a qualitative process. We're not going to use an engineering analysis, but rather something that anybody that applies their mind to it can make a decision. And we use the Likert scale. I'm sure most of you are pretty familiar with that. Certainly anybody that's undertaken a survey that's not a scientific survey is used to the scale. So looking at the probability, how likely are we to have an accident or an incident? And we'll score that from a 1, it's highly unlikely, and we'll move through, it's unusual, it's possible, right up to number 5, it's definitely going to lead to an issue. Then we have the exposure, and once again, we have a look at how often that exposure takes place. Is it rare? Is it less than once per year? Is it unusual? You don't really expect it. Is it perhaps occasional, and that might be weekly we have that exposure, frequently, once a day, and then continuous. So obviously the score is going to run higher the more likely we are to have that exposure. And then we have the consequence of an incident or an accident, and how severe is the outcome of the event. A 1 will be we notice it, but it's not really significant. And then we add to all of these, you can also score it as a 0, but if you score it as a 0, there's no risk. So if any one of these has a 0 score, it clearly is not something we have to address. So 1 will be a noticeable outcome, and we'll move up the scale to significant, to serious, to severe, where the facility is closed down, and then to catastrophic, where we'll end up with fatalities and significant destruction. So a relatively easy way to assess the 3 parts of that risk. And then we can come out with a score. Obviously 5 times 5 times 5 is 125, and 100 points, or call them whatever you want to, makes it a very, very important thing to address. You have no business, no right to be operating the chamber if you have something that sits at 100 or above. And then most of these risks are important. So we might stop the chamber if we have something between 50 and 100, stop the treatment I should say. Between 20 and 50 we should pay attention and perhaps put in some measures such as procedures and emergency ways of finishing that treatment, but we really need to fix that. And then the number 4 means that we need to address this in the longer term, so perhaps we will budget for it, perhaps we will train our staff in a different way, and then anything less than 5 is a risk that we can live with. The outcome of the patient is significant, the risk is not significant, and our decision will tend then to continuing as we are. And Jacek did ask me to just mention to you at this particular stage that we're going to try to use this scoring system in the new version of the European Code of Good Practice, so that we can not just have a list of things we have to do, but we can define how important those things are to our particular facility. So, what we're really proposing to you and to your team in the facility is you need to take responsibility for your decisions. And we can either decide that it's important, or we then realize we can't really get past this and we have to then issue some exception. And when we issue that exception, clearly we need to do it in a scientific and a professional and a realistic way. Interestingly enough, we can stand here as engineers and be proud of what you see there. In terms of equipment, this is generally not our serious area of concern. The engineers do a fairly good job, the installers do a good job, the people that do the commissioning and the training, and we don't really have significant issues. And most of our accidents, and I'd like to say all of the accidents, have not come from an equipment issue per se. It's the operation. It's how do we operate the equipment that has led to almost every single accident that we've had. This is our major risk area. This is where we should pay attention. I'll put this back to you. This is where you're involved in actually the safety of the facility. Of course, we have staff that become complacent. We have staff that rotate out, and we have to keep our training up to date to make sure that anybody that's in the facility has a good understanding of what the risks are. And the approach that we're using will address both of these areas. We tend to fixate on the technical issue because we have this chamber full of air and we have a fire risk, but we forget that it is us that causes the accident, not the equipment itself. Okay, let me share with you the experience that we've drawn out over the last 16 or 17 years. And this is now my own experiences. I've used 2 publications to do this out in the field. The blue one is a clinical approach to clinical hyperbaric facilities, a little bit more in detail, taking into account that the patients are not divers, they're not used to being pressurized, they're people that are ill, and they are different in how you approach them to how you might approach a diver that has at least had some experience to pressurization. And the green one is the one that we use to assess remote facilities where we don't have the infrastructure, the hospitals, the support, the staffing, and we still need to then treat those divers, and we have a slightly different approach to that, although both of them are clearly based on risk assessment. And then we've applied this around the world, and you can see right from Papua New Guinea in the east to California on the west coast, Cabo San Lucas, and then the Galapagos Islands. So pretty well covered most of the popular diving areas around the world. All the areas where a patient might be evacuated then back to. And this is the first clinical facility that we established in South Africa back in about 1998. Struggled along with old chambers. Dr. Frans Cronje was the medical director, did a lot of really good work, and were the founders to what we have now in terms of our modern commercial hyperbaric facilities. And the physician that bought that facility has put in 2 brand new chambers and already paid them off in the last 2 years. So that facility has really grown and it's doing very well. I'm from South Africa, so I can share the South African slides first with you. But you can see we have a range of chambers look very similar. The one on the top left is a chamber made in South Africa. Somebody thought that they could compete with the international market and make a homegrown chamber. You can see very rudimentary, and it's one of a kind, and at the end of it the company actually went bankrupt. And then we have a range of typical Monoplace chambers. Not really what you would see in Europe now. Our funding model is mostly from private and private medical insurance companies, and they're not that willing to support the treatment that we do. And then in terms of East Africa, you might recognize the one on the left, it's the chamber in Reunion, but we have chambers in Seychelles, Madagascar, Zanzibar, and a couple of the other areas that are popular in the warm waters of the east coast of Africa. Just a moment to share with you that in 2001, when we first published the first book and started to meet colleagues on an international basis, Mauricio Moreno came straight to me and said, listen, I've got chambers all over the world. I really need, as a person that sits in the States, I need to know that my facilities around the world are safe. And that's really where I started the international effort to assess facilities and see if I could educate the people and empower the people to accept what their risks are once they understand what it is they're dealing with. In the Caribbean, very popular diving area, we'll have some very basic chambers. And then a lot of what we call hand-me-downs. One on the right is an old Dutch mine warfare chamber made of stainless steel, donated to one of the islands. And then right down the Galapagos Island, for anybody that really wants to go to a remote area where access to facilities is many hours of flying, we have a facility that doesn't treat many patients but is essential to the safety of diving in that region. I think most of you know about the Red Sea in Egypt, not that popular at the moment, but certainly in the past used to treat many patients. And on the top left is Dr. Adel Taher's chamber. Never mind being covered with stickers, he's done a lot of hyperbaric treatments and certainly has a huge wealth of experience in treating divers. And once that chamber was working in the early 1990s, then we had a whole range of other chambers springing up, some of them locally built, some of them imported, all along the coast of the Red Sea. And all standing empty at the moment, sadly. And then we're in Europe, so just to give you a range of the type of chambers we might find here, some of them you might know, some of them you might not know. The top left is the Russian-built Monoplace chamber, what we call the Khrushchev chamber. Some of them built in the country, and then some of them built by countries here in the main part of Western Europe. And then a couple of other ones, and you can see with time these chambers have increased in terms of size and increased in terms of the ability to support some of the intensive care patients that come across. And then some of them, as you see on the bottom left over there, on a dam in Eastern Europe, probably don't ever see a treatment, and yet they need to be functional and operational. And then see that Dr. Fry is here. We can show a picture of Günther Fry in a pair of shorts and in the Maldives. Because mostly high-end clients are traveling to these islands, if they do get bent, we really need to treat them then and there. We can't afford to fly them back to Sri Lanka or somewhere else. And so several of the islands have a chamber just located there to treat people in that diving region. And then lastly, just to share with you a country that was growing very rapidly until about 5 or 6 years ago in hyperbaric medicine. The chambers were springing up, and they went from 4 or 5 chambers to about 80 clinical hyperbaric chambers, and now the numbers have started to come down. The only other comment I'd like to make is Dr. Peter McCartney wrote a paper on the colour, the preferred colour of a chamber, what would be soothing to the patients and acceptable to the patients on the outside before they enter the chamber. And I don't think that bright luminous green would have been a colour he would have rated as suitable. But we get different approaches to things. What do we learn out of all of this? Firstly, we see a huge variety of chambers out there. It doesn't mean that they're not safe. We just see chambers that are built in that country to the traditional Western European chambers that people operate. About 95% of all chambers out there are built to some existing pressure vessel code, and very unlikely we're going to have an issue with them. It's not the money that determines the quality and the safety of the facility. It's the staff. Led by the medical director, they have pride in their work, they're committed to their work, they're properly trained, and they're the ones that make a difference to that facility. And I've seen facilities that are very modern, huge amounts of money invested, 5, 10, 15 million euros into a chamber, and I wouldn't send somebody to that chamber. And then I've seen some very rudimentary chambers in remote areas where the staff are so dedicated and so well organized and trained that I would rather be exposed to that particular small, uncomfortable chamber, but I would feel more confident about it. And to be a little technical, just take a look. I'm not sure the top slide does the situation justice, but we see some interesting things out there, most of them based on ignorance. So we have chambers that have never been tested since they were installed in there, windows that are 20, 30, 40 years old, and generally in Europe we have a 10-year lifespan. In the United States we can extend that to 20 years, and some of us would take the windows further than that, but we base that on objective inspections, and we'll find very old, undocumented windows in the chambers. We have gas and piping systems that are a real mess and a nightmare, and they are just waiting for somebody to make a mistake. We have chambers in remote areas not fitted with some means of the patient or the tender being able to escape if the operator on the outside is not there. Please don't for a moment think that that doesn't happen. There were 2 cases, the one in Peru and one in Mexico. The one in Peru, when they had the fire inside the chamber, the question was, where was the operator? And her answer was, well, I leave the patient inside there and I go across the road to the canteen to get my lunch, leaving the patient completely on his own inside the chamber. That particular case, the report says that there was free flow on the mask. It was an airflow chamber, Monoplace chamber, and he was trying to get the attention of the operator by pushing the push button on a clearly hyperbaric safe communications device bought at some local hardware store, sparking every time you push the button, and eventually very dramatic fire, but nobody was there. And then we had the one in Mexico more recently where they forgot about the patient in the chamber, went home the next morning when the family came to find their father, they then realized that he'd been locked in the chamber and left him there. The safety valve I'm trying to illustrate up there for you is not sure how well you know how a safety valve works, but essentially we take the pressure from the chamber, we have a spring on the top of that, the spring is set to the pressure in the chamber so it will only open above that particular pressure. And in this particular case, in a relatively modern Western chamber, they've installed the safety valve on the outlet side. So the pressure now goes into the safety valve and makes sure it's closed. And the deeper we dive, the more that safety valve is going to seal. So clearly just lacking education. Fire suppression, some of the facilities have very good fire suppression systems that are not tested, and when we test them after 10, 20 years, they all block up and they're going to be pretty useless in the event of a fire. And then we have no fire extinguishers in some chambers, or the maintenance is totally lacking. You might be able to see from the middle picture over there, that's my hand. I've actually taken out the entire nozzle section of the fire extinguisher. It's a water-based air-filled extinguisher, but you see it still needs pressure. So every day when they do the inspection, the fire extinguisher is full of gas, there's no problem. Meanwhile, the gauge has failed and stuck in that position, which gauges do. And the assumption was that the fire extinguisher was functional. So really important to test this stuff. And then we have electrical issues, mostly very poor wiring. Sometimes we have frayed wires and loose connections lying on the chamber, a significant piece of steel, so being able to end up with short-circuiting there. Inadequate reserves in terms of power and gas if there's a shutdown of the services to the facility. And then a range of administration and management issues. The one on the very right-hand side, just pay attention to that word because it's going to come up in a moment. You'll see how significant that is. And then very poor maintenance. Sometimes they'll do the maintenance, but they won't document it, and sometimes they just don't do it because these chambers are robust and they can work for 20 years without a problem. But then when they have a problem, it's a significant issue, and then if you don't have records, you can't show that you did the maintenance. Big issue in the Florida fire. Chambers were claimed to have been maintained. Clearly they were not maintained, they had a fire, and one of the things that came back to haunt the doctor and the safety director was the fact that there were no records for the maintenance. So it catches you out at the end of the day. We took 105 of these facilities around the world and analyzed them on a basis of what were the typical risks that we determined. There were 82 common risks that are applicable across the whole range of chambers. We then looked at how frequently those particular risks occurred in the sample set of 105, and we came up with what we call a risk score for each of those elements that were present, the risks that were present. And to get the score, we had to look at the fire risk, the mechanical risk, the physiological risk. That's not just one number. And we came up with a score that could then indicate which are the most significant ones and which are the least significant ones. And you'll see number one on the list that occurred in 85 of the 105 chambers. They did not have, or they had totally adequate drills for safety procedures. Let me share another practical thing with you. I'm on an island assessing the chamber. Very nicely put together chamber, really competent doctor, never mind the rest of the staff. And I asked the doctor, she was a rotation doctor that, they have this rotation system because it's very difficult to leave one person at the chamber for the full year. And I asked her an innocent question, when you have a fire in the chamber, what are typically your steps? Interestingly enough, when we have a fire in the chamber, it is not the fire deluge system that puts out the fire. It shuttered with the oxygen. I was waiting to see that she'd answer that question, that she understood what feeds the fire and what extinguishes the fire. So she said, no, we have a procedure. So I said, well, can you tell me the first 3 steps? She said, yes, it's documented, I'll get it to you. So I said, no, I'd like you to explain it to me. She said, no, it's on a document. So she goes off to the filing cabinet, it's here somewhere, and she's looking through the shelves. And of course, as an assessor, I get very suspicious when somebody can't find something, because it usually indicates they either don't know or it's missing. So it's not there. So she said, I know where it is, it's on the computer. So I've listed under the safety procedure. So I said to her, you have a fire in the chamber, and your fallback position is to go to the computer to see what you should do. That's completely adequate. So it's really important. It affects us on a global basis in terms of the safety of our facility. And then we took each of these 82 findings, took their scores, added those scores together per chamber, and now we could get a risk assessment score for each of the chambers. So we did this on a blinded basis. I couldn't see the name of the chamber. I just came up with what the score was. And I wasn't trying to rank chambers from the least safe to the most safe. I was trying to look at patterns and what are the most significant things that we find. And they're very interesting. Medical supervision. Should we have a doctor on site? Or can we have a doctor on call? Or with respect to commercial divers, they believe they know more about treating patients than a doctor does. And clearly, when they're offshore and they're doing routine surface decompression, you don't need a doctor there. But when you have an injured person, it's a medical treatment, and you need to have a doctor right at the facility. And you can see the significance between having a full-time doctor versus even a doctor on call, because on your vertical axis, as you increase the number, your facility becomes less safe. So the safest facility is a facility where there's a full-time doctor available at the chamber. Training of staff, and Peter Atke spoke to you yesterday about training. When we look at formal, or what we mean certified training, the person is trained properly to proper standards that are referenced to international standards, and they sit some form of examination or test, and they're then certified as operators. Significantly safer facilities than even the on-the-job training, which is not formal training. By on-the-job, I mean the person arrives at the chamber and somebody explains to him what he should do, and when he makes mistakes, they correct his mistakes, but there's no proper pattern of how they're trained. And then we do have chambers where there's no training. Either the doctor has no idea as to what happens, or the operator has no idea what happens on the inside of the chamber, and likewise, the tender on the inside has no idea what's happening on the outside. So you can see very significant differences between these. Then a question that you debate amongst yourselves. I have no right to tell you on a medical basis whether one should give a table 6 or a 20 meter seawater treatment versus a Comex 30 or 30 meter 100 foot seawater treatment, or a table 6A. Fortunately, it's becoming less and less prevalent. Never mind the location. So whether it's Western Europe, United States of America, or some really remote place, you can see that the treatment table 6 still remains the safest option from an operating point of view, from an equipment point of view. This is not looking at the medical outcome of the patient, but it might be interesting for you when you weigh this up. You have physiological issues with the table 6A, with a very deep table, but you also have safety issues. And then number of patients per year. Clearly, the less patients you have per year, the less experienced the people are, the less on top of their knowledge they are, and you can see quite a significant change. Higher number, less safe facilities versus facilities treating more than 50 patients per year tend to be a lot safer. Not completely safe, but certainly a lot safer on a relative scale. So that's our risk assessment, and as you can see, I've done 144 chambers now around the world. We have a really good database and a good understanding as to how real these things are, and which ones are prevalent and which ones are theoretical ones that we still hammer home in our codes and norms and standards, but actually they are irrelevant to what happens out in the field. So once we have analyzed and assessed our risk, we clearly need to fix it. We call this the risk mitigation. And traditionally, we'll either make an engineering change, if it's something based on the technical aspect, if it's how we operate the chamber, the interaction between the physical aspect and the patient. We can then change procedures, look at other ways to improve safety. Or if we can't do that, then we have to put physical barriers in place. We cannot change it, we cannot use a procedure to ameliorate it, we then have to do something physical in that case. So our typical mitigation strategies are to eliminate that risk completely by removing it, or sometimes we might have to stop the treatment until that risk has been removed. We can substitute, we can use something else instead of what we're using that has a lower risk score. Clearly we can do some engineering. It doesn't mean that I do it, but technical stuff that can be done at the facility. And again, that might be putting a barrier around where the intake to the compressor is to prevent motor vehicles actually parking there and polluting the gas going into the chamber. Administrative controls, really important that we can change the instructions, change the training, add procedures to our facility. And then finally, we can issue people with protective equipment. That might be a person working in the compressor room needs to wear hard shoes and needs to wear hearing protection and eye protection. And very often we have all this equipment given to our staff, and when we come and assess them, we can see them walking to the compressor room with a 95 decibel average sound level inside there with the hearing protection still sitting around their neck. It's a great photo that I have in one of my other talks where the operator has the earmuffs around his neck and he's in a very, very loud area. So we have to keep training people to make sure they use it. I'm going to give you two brief examples over here of how we apply this process in reality. For those of you that use oxygen dump masks inside your chamber, we know that when we're breathing out the oxygen, which gets dumped outside the chamber, we have a significant risk in that if that equipment were to fail, we would expose the patient's lungs to a significant suction injury. And so we have a requirement to install some protective measure between the patient's exhalation system and the pressure on the outside of the chamber. And the technical term we use for that is some form of a back pressure regulator that adjusts for the depth of the chamber, but keeps the suction pressure on the patient to a constant half an atmosphere or whatever they decide it needs to be. So what do? We come across a chamber where there's no back pressure regulator fitted. Do we stop the treatment? Do we have to wait for some engineer to come in and weld in or penetrate in the chamber? So how do we tackle this from a risk-based point of view? Can we operate the chamber safely without a back pressure regulator? When we analyze the actual situation, you can see from the picture, this is a typical, what we call a Scott mask. It has a dump regulator, exactly the same as our scuba regulators when we exhale. And the manufacturers publish that when they have a failure of this particular regulator, so when the suction pressure is too great, the diaphragm will tear. If the suction pressure is lower than 3 atmospheres absolute, the actual diaphragm just closes. So we don't expose the patient to hazard. The patient will just then battle to be able to exhale. So if we then, and our motivation is then we change our treatment modality to only maximum 388 treatments, then we know that regulator can never fail. And then we might bring the operating pressure of the chamber down to 388 by adjusting the safety valve, and that way we will not end up with an exposure. The theory is still there, but we've removed the possibility of an exposure. The medical director takes responsibility. He or she clearly needs to endorse that waiver, and then please, we need to document every decision we take, because if there is an accident, this is what's going to be our get out of jail pass. Monoplace chambers are not that prevalent here certainly not in Western Europe, but there are 3,000 facilities in the United States alone, never mind the ones in Japan and in China. The risk that we have in this particular, the hazard that we have is switches. So we need to do something with the switch, and the inside of the chamber clearly is a hazardous zone if the chamber, or especially if the chamber, is filled with 100% oxygen. So the rules tell us you cannot put a switch inside the chamber. There's a risk of sparking, and the answer is you may not. But we need switches. Okay, in this particular case, you need a patient call button, so the patient's not pushing on the buzzer of the non-compliant communication system. And we can do this pneumatically as we did in the past, but we've moved ahead and we're trying to be more sophisticated. And then in some of the deeper diving chambers, you want to have volume control, and in the Monoplace chamber, because as the deeper you go, there's a difference in the sound quality, you might want to adjust the volume instead of telling the operator on the outside to turn up or turn down the volume. So the question is, the rules say you may not, but can we then install a switch inside the chamber? Times have changed, and so we have the advent of the button that we use almost every day when we go into an elevator. So it's essentially no moving parts. It does not have a spark that it can induce because it works on the induction of our finger when we touch the thing. So it's a touch button. Everything that is electrical happens outside of the chamber, and I know that some of my colleagues in the United States say the rule says you cannot, and I try to explain to them, but there is no risk, and they say no, we still follow the rules, but hopefully we are a bit ahead of that. So our motivation is it's intrinsically safe, we cannot have a spark, there's no reason not to install this. Once again, the medical director has to endorse the decision we've taken, and of course we document this. So we've applied the similar risk mitigation to some of the things I shared with you a few slides back. And the chamber that has no documentation or has no nameplate, are we going to allow this to continue? And there are various ways of using inspection and tests to bring that metal chamber back into what you call certified service where we know it's safe. So it doesn't mean you replace the chamber. You just do some analysis, some tests, some inspections, install a new nameplate, and your chamber is good to go. I'm not going to read every one out to you, but for each of the risks that we've identified, there are relatively simple workarounds, and they're based on comprehension and some empowerment of the staff to understand it, but they are always based on what is the actual risk, not just what is the theoretical hazard that comes up in the literature. Once we've done Our mitigation step, we then really need to monitor to make sure that the decisions we took, the actions we took, are having a positive effect on the safety status of our facility. And this is an administrative process, but we're really trying to determine the effectiveness of what we've done. Very important not only to record actual accidents, those are too little too late events. We need to record our near misses, meaning we did something that wasn't right or there was some incorrect exposure. We didn't have an accident because the probability was too low, but still, in certain circumstances, that could have led to a dramatic accident. And so those near misses are really the most important things that we would record. And then to do any analysis, we need to have some form of denominator data. So it might be your number of treatments, your number of patients, the number of cycles your chambers go through. And then an appeal to you, I know scientists love to measure for the sake of some theoretical outcome. We don't just measure for the sake of measuring, we have something that's some objective that we would like to achieve. Okay, so we know about chambers and we know about the risks about the chambers, but we have constant new challenges that come up to us or that we're faced with. And here's a very, very pertinent one, because I know in Europe the situation's changed and some of the pumps and things are no longer available. They're no longer available as certified for hyperbaric use. Many of the new devices that come on the market were never designed or intended for hyperbaric service. We have existing devices that the manufacturer withdraws or has some liability concern and no longer wishes for us to use it. Or that manufacturer might say, I'm withdrawing my approval, which means that we then operating that equipment without the manufacturer's endorsement. There is an accident, we're the ones on the firing line. Then we have CE marking issues. We have very low volumes of equipment, and still we're still required to get some form of approval, and that means the price of that equipment is going to be radically elevated. And the question is, can we find alternatives in terms of certification of this equipment? And I've just listed two very common ones. The Federal Drug Administration in the States give a pre-marketing approval to equipment, very expensive process. And the equipment manufacturers don't want to go down that path because there's a liability exposure and there's a lot of money spent to get that FDA approval. And in the therapeutic goods in Australia, they have a similar process to make sure that medical equipment is certified for use. But we might think there are many chambers, but in terms of the number of products the manufacturer makes, they're really insignificant. I apologize for all the text, but this is a legal interpretation taken from the FDA's requirement for labeling a particular device or a drug. And I'm introducing it to you because this is probably one of the strictest countries in the world is the States because of the intense liability issues. And the fear amongst the physicians is that if we don't have FDA approval on that device, we cannot use it. But the legal interpretation from the FDA basically says that if the physician decides that the risks in that particular case are things that they can contain, they are satisfied, they understand what the risks are, they analyze the risks, and this is going to have a beneficial outcome on the patient, then it becomes a physician decision to use that equipment off-label. So physicians are allowed to use pumps and ventilators and other devices that were not designed for hyperbaric applications, as long as they do a proper risk assessment and document how they got to that particular decision. And whether that will work in Europe with the Medical Device Directive, I don't know. The idea here is that the physician in their facility purchases a device that has a particular label of use and makes a decision to use it off-label. So the manufacturer is no longer involved in this process, and the manufacturer clearly is going to say, you're on your own. But as long as we don't do that for commercial purposes, the laws in the States will protect that physician from making a decision that the physician thought at the time was appropriate for the outcome of the patient. And how do we go about scientifically evaluating this? We have a decision tree that has been published, that we put together for the NFPA, and it's based on a couple of really basic steps. And proper needs assessment: do we really need this piece of equipment? What exists in the literature about this equipment? Then we have to analyze what are the key areas of concern. Where do we need to really focus? Are there push buttons that could depress under pressure? Are there things that are affected by density? Are there fire risks in there? And we do a HIRA, a hazard identification, a risk analysis, a risk assessment, to make sure that our identification of that hazard is a real risk to it being operated in the chamber. And many times it is not. But still we have some fear, and we need to alleviate that fear. We do need to comply with the codes and standards only in the context that when they limit us to electrical power, temperature, noise levels and so on, that we comply with those occupational set standards. They're not intended to be stumbling blocks, but we do have some occupational health standards that we need to comply with. Then we need to make the changes and then clearly function test it, make sure it functions under the range of operating conditions, and then document the process and review that process and have it endorsed internally in terms of the facility and perhaps some form of peer review outside the facility. And that's published in the NFPA, so it is really something that in the States have allowed us to start embarking on the process where we do off-label work, but we have a way of making sure that it is safe. And then we have a topic that is important to us. We have, I'm not sure how many countries in Europe, maybe 25 or so, and we probably have 25 different healthcare accreditation programs. But accreditation is important to us. It makes sure that the work we're doing can be recognized by our colleagues, not only in our country, not only in our facility, but either nationally or even internationally. So it is an important thing for us to do, but usually it is done on a compliance basis. The assessor comes in, has a checklist, makes sure that you comply with the checklist, and then says you're accredited. Our approach to that is, but it doesn't account for that facility being different, and we would rather do it on the basis of, are there real risks that haven't been addressed, or is that facility properly designed, properly operated, that you can ensure the quality and the safety of the facility. This is a model I presented at the meeting, ECHM meeting in Belgrade several years ago, and again credit to Jordi De Sola, because this was a diagram he essentially drew out and put on the front of the European Code of Good Practice. But I've taken it a few steps further. We have a hyperbaric chamber at the bottom, and we have certainly codes and standards that tell us how to design and commission that chamber to make sure that we have a safe chamber. The pressure vessel is safe to use. Then we have existing documents and an existing certification program for the hyperbaric system. Everything that goes around the chamber, the gas supply, the electricity supply, the compressors, and so on. And that makes sure that we can give a safe and effective treatment. Then we start getting into the interface with operators in the chamber. We call that the hyperbaric facility. So it's all the treatments that are given in that particular facility. But we're not looking yet at the patient. We're looking at the staff, their training, their competence. And again, there are ways to certify this, but now we're getting a little more cloudy. We don't have a really good way of accrediting different facilities. But this will certainly make sure that we give good quality and safe treatments. And then the last level of accreditation, which most of us are used to, which is the healthcare facility or the hospital accreditation. We have ISO 9001 and various other models that we will use to determine the accreditation program we're going to follow. And we have the International Joint Commission from the United States that is applied to many hospitals around the world. And that's really where we're focusing on giving good outcomes to our patient, properly educated patients, making sure that we can take care of our liability issues. But that's really the level that we can then compare facilities one against the other. On the vertical axis, you can see an improvement in the outcome of the patient and the safety of the facility. And on the horizontal axis, you can see it costs us more in terms of resources, in terms of time, in terms of money, but we need to commit ourselves to additional work to make sure that we get our facilities safe. But really, we could look at codes and standards. The only way to get a safe facility is through what we call a safety culture. You cannot have a safe facility unless management are committed to that particular safety program. I'm an ISO 9001 assessor for myself. I don't actually like doing those assessments. But one of the boxes we need to check and discuss is management committed? And of course, management's committed to safety. That's why they delegate to the safety officer and say, you do it, and then come to me when it's done and I'll sign off. That's not commitment. Then we need for everybody to understand what the risks are and to share in that understanding so that they can understand what is the impact on the people going to be if we don't make sure that we operate safely. We need to educate our staff to what are the realistic and the real risks we're going to encounter in our facility, and that allows the staff then to feel that they can take responsibility for their decisions. And then finally, we need to monitor this continuously reflect on our processes, and that's how we develop what is called a culture of safety, and that's the cornerstone of the safety in your particular facility. It doesn't happen overnight. It's a process, and usually it follows the development of that facility as people become more exposed to it and they become more comfortable with what they're doing, so they will tend to get to a point of maturity where they feel they're comfortable enough. Not they're complacent, but they're comfortable enough. And you can see that typically a new operator will come into a facility and feel overwhelmed by the issues, and by the time 3 or 6 months has passed, because they do it on a daily basis, they feel a lot more secure. You need to empower your personnel, not just send them to a training course, but make sure that they understand what it is that they're dealing with, and that way they will lead to competence. Not through writing an exam, not through experience alone, because we can do the wrong thing over and over again and gain experience, but that doesn't give us competence that we require. And then, at the end of it, if we don't understand what it is we're dealing with, we really have no hope in getting that facility to a safe status. Just to conclude, what I started the first slide with and what I'd like to finish with is, we have to some extent a desire for formal accreditation, formal compliance, versus an understanding what the issues are, a distillation of the real risks and analysis of those risks, and decisions taken based on what is unsafe rather than what box we need to tick. I know there's pressure on us to tick the boxes in formal compliance, but what I'd really like to say as my last part of the message is, compliance does not make your facility safe. Compliance means you tick the boxes. If you don't understand what it is you have in your facility, then there's no chance that your facility can be safe. Thank you for listening, and any questions you'd like to ask.